Welcome to a lesson with Dr. Powell. Let's look at how we can express the remainder of a Taylor series. But first, let's look at another way we can build a Taylor series. Start with a function and make a very simple equality, assuming the function is defined at 0. And then we're going to interpret this part as an integral. The integral of the derivative of f. So the f is the antiderivative. And notice we're evaluating it at x and 0 and subtracting. So it should be a nice equality. That's how we do this. We take the antiderivative and plug in the endpoints and subtract. But what do we plug in here? It's not x because x is an endpoint. So we choose whatever we like. We'll just choose t. Okay. So this nice equality that we have right here for f of x is very nice. We can repeat it on f prime as follows. 0 to x, and then we have f prime of 0 plus an integral, keeping this in here, replacing just f prime here. Thinking of what we did over here, notice how we plugged in 0 to f, we're plugging in 0 to f prime. And then notice how we had an integral from 0 to x, and we're plugging in x. We're going to have an integral from 0 to t, where we're plugging in t of the derivative of f prime, which is a double prime, of anything we like, but not t and not x. Those are bounds already, so we just choose something else like t2. Okay, and that's in there. And then we have this with the dt. Okay, now we're going to repeat this process one more time on this, but before we do that, let's split this in the dt integral up into two parts. Okay, we're going to get integral from 0 to x, f prime of 0 dt, plus integral 0 to x of this other part right here. Okay, 0 to t, f double prime of t2, and then we have dt2, and we have dt. All right, so this part's going to be inside of here. All right, now how does this evaluate? Now this is a constant, we're plugging in 0. The antiderivative will simply be f prime of 0 times t, the variable there. Throwing in the bounds and subtracting, we just get f prime of 0 times x. 0 plus that, plus, okay, what happens here? Now, if we repeat this process, notice that we're going to get an f double prime of 0 plus another integral. So let's consider and think about what's happening right there. Okay, let's erase this part up here. Just remembering what we have is an expression for f of x. Okay, so we're going to have, let's just look at this part right here. We're going to have an integral 0 to x, 0 t, and then we have f double prime of 0 plus an integral of from 0 up until t2, which is what we're plugging into f double prime, of the derivative, plugging in a new variable, and dt3. Okay, and all of that as a dt2 and a dt with this kind of nesting right here. So this integral with that dt, this integral with that dt2. Now, what's going to happen right here? Notice we're taking antiderivative with respect to t2 and then to t. And our bounds are changing from from 0 to t to 0 to x. Now, when we take an antiderivative with the first one, we're going to get f double prime of 0 t 2, because that's this one. And then we evaluate from 0 to t, and that'll, when we throw those in and plug in, we're going to end up just getting that for illustration, we'll just think we have 0 to t. We plug in t, plug in 0 and subtract. We're just going to get this out of it for this first integral. For the next one, notice this is a function with respect to t. Take its antiderivative. We're going to have a t squared divided by 2. And then we evaluate this from 0 to x. And we end up getting f double prime of 0, x squared all over 2. Notice for a Taylor series or power series, centered at 0 for this function, these are the first few terms. Constant, this guy, this one, and this one. We've successfully gotten it. The next part of what's left over represents the remainder. That's why I expressed it this way. In fact, we need these two guys right here to come over here to this part to intermingle with this one. Following in a like manner, over here, let's just see what's going to happen. All right. As we're going along on this part, we have f. We could repeat. In repeating this process again and again and again, let's think. This right here, if we could have a bound for the third derivative, let's suppose that the third derivative at most is something like a capital M. That's the biggest it can be. All right. So if that's the biggest it can be on this interval, then that means this whole part right here with these two guys in here is actually bounded above by this, by just throwing an m in here, replacing the function. Because you think about this, if the third derivative is a function that looks like this, and m is a function that looks up here, what happens when we take an integral? The integral underneath m is bigger than the integral underneath the actual third derivative. So if we just simply replace this f triple prime with m, we'll actually get a remainder expression term that's bigger than the actual, and we can bound it. So what we do is we just simply take that third derivative, replace it with an m, and then we go through and repeat this process. And what we're going to do is we're going to get something that's going to bound the remaining terms to add. Okay, so let's see how that would work. Okay, so what we end up getting is, what we end up getting is first we evaluate this dt3 with a constant. And that's simply going to be mt2. Thinking of a constant and you have a t3 and you evaluate from 0 to t2, throw in the t2, it's going to be something like this. Now with the next integration, we're going to integrate, take an antiderivative, and throw in the bounds. And when we do, this 2 will just be a t. Next, do the same thing over here, take another antiderivative, we're going to get a 3, and we multiply by another 3 right there. Okay, and then we throw in x as a bound. 0 as a bound will go away, and then we just get that. So in other words, that's the remaining. That's the remainder. X represents the distance away from the center. M represents how big the third derivative can be, and this is simply a factorial. So in general, if you want to bound the remaining terms that you have not added in a Taylor series, you can always do this, just with a little generalization. What we do is we think bound for nth derivative, a constant bound for nth derivative, Then we take distance to center, and we raise it to the nth power, where n is the same as the derivative you're talking about. And then you divide by n factorial. All right. So this is going to bound the Taylor series that actually adds up to just the n minus first place, because this is like the beginning of the remainder. Now, if you want to be technical, suppose you could want your Taylor series sum to end at a number n, which would just push this up one. N plus 1, n plus first derivative, n plus 1, and you could think of that as n plus 1. All right. So that is the derivation for the remainder formula for Taylor series. Thanks for watching.